Hello everyone, this is Dr. Anandi. I was earlier working in Mumbai. Now I have shifted to Singapore. I have written a paper in IJSR in the year 2014. It's Joining Delay Packet Delivery and Limitations of EGMP. Now let us see the abstract. A novel, efficient geographic multicast protocol, EGMP, is proposed. A network-wide zone-based bidirectional tree is used to achieve efficient membership management and multicast delivery. An efficient distributed algorithm is used that support dynamic changes to the multicast group during tree building and allows overlapping join and leave operations. It uses a hierarchical structure to implement scalable and efficient group membership management, and a network range zone-based bidirectional tree is constructed to achieve a more efficient multicast delivery. It does not depend on any specific geographic unicast routing protocol. Introduction. An efficient EGMP is designed to be comprehensive and self-contained, yet simple and efficient for more reliable operation. It includes a zone-based scheme to efficiently handle the group membership management and takes advantage on the membership management structure to efficiently track the locations of all the group members without resorting to an external location server. EGMP makes use of position information to support reliable packet forwarding and could easily and quickly build packet distribution paths and reliably maintain the forwarding paths in the presence of network dynamics due to unstable wireless channels or frequent node movements. EGMP can scale to large group size and network size and can efficiently implement multicast delivery and group membership management. It uses a hierarchical structure to achieve scalability. Structure. The network terrain is divided into geographical non-overlapping square zones, and a leader is elected in each zone to take care of the local group membership management. A zone-based bidirectional multicast tree is built in the network range to connect those zones having group members, and such tree structure can utilize the network's resource efficiently. EGMP can scale to large group size and network size and can efficiently implement multicasting delivery. Related work. In this paper, zone-supported geographic forwarding is introduced to reduce the routing failure and provide mechanism to handle zone partitioning. In addition, we introduce a path optimization process to handle multiple paths and provide a detailed cost analysis to demonstrate the scalability of the proposed routing scheme. EGMP does not make any assumption of the network size in advance, and the change of the membership of a zone does not need to be sent to a far-away RP, but only needs to be updated locally. Instead of using one RP as a code for group membership management, which may lead to a point of failure. EGMP introduces the root zone, which is much more stable than a single point and manages group membership more efficiently within the local range. It uses more efficient zone-based structure to allow nodes to quickly join and leave the group. It also introduces root zone and zone depth to facilitate simple and more reliable group membership management. EGMP does not use any periodic network-wide flooding. Thus, it can be scalable to both the group size and network size. EGMP supports scalable and reliable membership management and multicast forwarding through a two-tier virtual zone-based structure. To reduce the forwarding overhead and delay, EGMP supports bidirectional packet forwarding along the tree structure. That is, instead of sending the packets to the root of the tree first, a source forwards the multicast packets directly along the tree. Now, how leaving an efficient geographic multicast protocol has been established. If there are multiple clusters in a zone, each cluster will elect a leader. EGMP handles the zone partitioning problem as follows. When an upstream zone leader receives join request messages from multiple leaders of the same zone, and the new message is not sent as a result of leader can handover. It can detect that the downstream has partitioned into multiple clusters. In case that not all the clusters of a partition zone send join request messages, the upstream zone leader may not be aware of the partitioning of the downstream zone. When sending a packet to the cluster, it uses the leader's position instead of the zone center as the transmission reference. Even though the leader may move, its position carried in join request message can still be used as a reference to forward packets to its cluster. When receiving a packet with the position of the leader as the reference, a cluster leader can learn that multiple clusters exist within its zone. When a cluster leader receives a packet distinct to its zone but does not match its status, it will send an update message to its upstream zone. When receiving messages from multiple leaders of the same zone, the upstream leader can detect zone partitioning. It will resend the previous message to the target cluster with the position of the zone leader as the destination. When the leader of a cluster changes, the new leader sends a joint request message to its upstream zone immediately, which also carries the old leader's address. What are the limitations of EGMP? At the upper layer, the multiple packets will flow along the multicast tree, both upstream at the root zone and downstream at the leaf zones of the tree. At the lower layer, when an on-tree zone leader receives the packets, it will send them to the group members in its local zone. In EGMP, the group members are not directly connected to form a tree. This will reduce the tree management overhead. The basic algorithm generates a correct tree provided the following conditions hold. The multicast group is known to all the participants. The multicast group does not change once execution of the algorithm has begun. Performance evaluation. We implemented the EGMP protocol using NS2 simulation. The following metrics were used for the multicast performance evaluation. Now, before that, EGMP supports scalable and reliable membership management and multicast forwarding through a two-tier virtual zone-based structure. At the lower level, in reference to a predetermined virtual origin, the nodes in the network self-organize themselves into a set of zones, and a leader is elected in a zone to manage the local group membership. At the upper layer, the leader serves as a representative for a zone to join or leave a multicast group as required. As a result, a network-wide zone-based multicast tree is built. The metrics which we use for the multicast performance evaluation are packet delivery ratio, which is nothing but the ratio of the number of packets received and the number of packets expected to receive. The next is normalized control overhead, the total number of control message transmissions divided by the total number of received data packets. The third one is normalized data packet transmission overhead, the ratio of the total number of data packet transmissions and the number of received data packets. And the last is joining delay, the average time interval between a member joining a group and its first receiving of the data packet from that group. In EGMP, we assume every node is aware of its own position through some positioning system or other localization schemes. In EGMP, the zone structure is virtual and calculated based on a reference point. Therefore, the construction of zone structure does not depend on the shape of the network region, and it is very simple to locate and maintain a zone. We'll see about the protocol overview. EGMP uses a two-tier structure. The whole network is divided into square zones. In each zone, a leader is selected and serves as the representative of its local zone on the upper tier. The leader collects the local zone's group membership information and represents its associated zone to join or leave the multicast sessions as required. As a result, a network range core zone-based multicast tree is built on the upper tier to connect the member zones. The source sends the multicast packets directly into the tree, and then the multicast packets will flow along the multicast tree at the upper tier. A multicast tree broadcasts joint request query messages to the entire network periodically. An intermediate node stores the source ID and the sequence number and updates its routing table with the node ID from which the message was received for the reverse path back to the source. A receiver creates and broadcasts a joint reply to its neighbors with the next hop node ID field filled by extracting information from its routing table. The neighbor node whose ID matches the next hop node ID of the message realizes that it is on the path to the source and is part of the forwarding group. It then broadcasts its own joint table built upon matched entries. This whole process constructs the routes from source to receivers and builds a mesh of nodes, the forwarding group. We focus on the studies of the scalability and efficiency of the protocol under the dynamic environment. Simulation environment and protocol performance. Here, we simulated EGMP protocol within the global mobile simulation, that is GlomoSim. The nodes are randomly distributed and move following the random waypoint mobility model. We evaluate the performance of EGMP with different node densities, moving speeds, and group sizes. EGMP performs better with higher node density. At high density, the collisions among neighboring nodes will increase and cause more packet loss. The transmission load of EGMP decreases much faster than ODMRP as the node density increases. On comparing the performance of EGMP with geographic multicast protocol, EGMP has lower control overhead, lower group joining delay, higher packet delivery ratio, lower data transmission overhead, higher bandwidth utilization, and higher performance. In EGMP, when a node wants to join a group, it will start the joining process immediately because of this joining delay is less. EGMP will have lower packet transmission overhead. In the conclusion part, EGMP makes use of geographic forwarding for reliable packet transmissions and efficiently tracks the positions of multicast group members without resorting to an external location server. EGMP has a significantly lower control overhead, data transmission overhead, and multicast group joining delay. Our simulation results demonstrate that EGMP has high packet delivery ratio and low control overhead and multicast group joining delay under all cases studied, and is scalable to both the group size and the network size. Here in this paper, the performance metrics such as packet delivery ratio, control overhead, packet transmission overhead, and average joining delay of the protocol EGMP is dealt. Our simulation results shows that EGMP has high packet delivery ratio and low control overhead and multicast group joining delay under all cases and is scalable to group size. We propose an efficient and scalable geographic multicast protocol EGMP for manage. The scalability of EGMP is achieved through a two-tier virtual zone-based structure, which takes advantage of the geometric information to greatly simplify the zone management and packet forwarding. EGMP significantly reduces the tree construction and maintenance overhead and enables quicker tree structure adaptation to the network topology change. Thus, I conclude that EGMP is more efficient. I hope all of you understood the content. Thank you so much.
Yeah.